Alright, probability plays an important role in genetics. For instance, sickle cell anemia is an inherited trait, which causes red blood cells to become deformed and not able to carry oxygen. A person with sickle cell anemia has the sickle cell gene from both parents. If a person with only one sickle cell gene will have a much milder and non-fatal anemia called the sickle cell trait. So let's take a look at problem number 7. So let's suppose two parents each have one healthy gene, which we'll have as capital S, and one sickle cell gene. I want to find the probability that parents will give birth to a child who A is healthy, B has sickle cell trait, C has sickle cell anemia. So what we're going to do is we're going to establish a table here. So I'm going to put parent 1 on top, parent 2 on the bottom, and let's see, you got one regular cell or one gene and one with a sickle cell, and we'll do the same thing for the second parent. So one possibility is that the child could get both healthy genes. Another possibility that from the the second parent, the gene's healthy, but they get the sickle cell gene from the first parent. Or the opposite could happen, that they get the sickle cell gene from the second parent and the healthy gene from the first parent. Or they could end up with the unfortunate case where they end up with two sickle cell genes. So there's 1, 2, 3, 4 possible outcomes. So that's our bottom number in each of these cases. Now there's only one way that the child could be healthy. So that's a 1 out of 4. Now there's two ways they can have the sickle cell trait, here and here. So that's 2 out of 4 or 1/2. And then sickle cell anemia, there's only one chance that can happen. So that's 1 out of 4. Alright, so let's talk about empirical. Unlike theoretical probability, the empirical probability event is found by actually performing an experiment over and over again and observe how frequently an outcome occurs. So empirical probability of event E is given by the observed number of times E occurs over the total observed occurrences. So basically, you perform the experiment over and over again, and then you just observe how many times a particular thing happens. And by the way, these formulas we've been talking about, they're on the back side of your formula sheet. So here's theoretical probability, and here's empirical probability. So let's turn to problem number 8 in our workbook. This is on page 146. So a fair die is rolled a number of times than the number of, let me try that again. A fair die is rolled a number of times, and the number of times a 5 occurs recorded below. Calculate the empirical probability. All we're doing here is just doing the division. So first time around, we have 3 over 10. As a decimal, that's 0.3. Second time around, we're going to do 15 divided by 100. And that will give us 0.15. Then we're going to keep going. Then we have 159 over 1,000. That's 0.159. And 1703 divided by 10,000. would be 0.1703. Now, if this die is truly fair, as I keep increasing this number should get closer and closer to 1/6, or 0.16 repeating. And we have a name for this. This is called the law of large numbers. Notice that as the number of die roll increases, it probably tends to approach the theoretical probability of 1/6, which is 0.1666 repeating. This principle is known as the law of large numbers. So let's go to page 47. And this should look very familiar. In a recent survey of 1,056 likely voters, people were asked, what is the most important problem facing the country today? Results are displayed below. This is exactly what we were doing earlier with the fractions in the previous section, but now we're doing a probability. So if a person's randomly selected from the participants in the survey, find the probability that the participant is a Republican. All we're doing is writing the ratio of the Republicans to the total. So we have 533 over 1056. Let's do that in our calculator. Make sure it's reduced to lowest terms. And that tells you it is reduced to lowest terms. It's not able to reduce it, but it gives you the decimal. So that's approximately 0.505. Find the probability that the participant said foreign policy is the most important problem. So foreign policy, that would be 98 out of 1056. So that should reduce. That should be a 6 there. So that's 49 over 528. And let's calculate the decimal. Set your double arrow key. It's about 0.093 if we round it off. Find the probability that the participant is a Democrat who said health care is the most important issue facing the country. All right, so my bomb number still doesn't change here. It's still 1056. But now we have to be a Democrat who said health care is the most important issue. So Democrat, health care is 123. So let's see if that reduces. So that's 41 over 352. So there's our fraction form. And let's get our decimal. So I'd round off to 0.116. So D says, given the participant is a Democrat. So now we're just looking at the Democrats. So this phrase here is going to change our bottom number. So we're saying we're now given that they're a Democrat. And the number of Democrats here is 523. Find the probability that illegal immigration was the most important issue. Well, there were 78 Democrats here that said illegal immigration was the most important issue. So we're going to put that over the 523. We'll check to see if that reduces. And that does not. Let's get our decimal. So 0.149. But again, notice that this is very similar to when we were going through and we were going ahead and writing fractions. We were doing an early section.